This is our last talk on light dark matter, and today we will finally see the missing energy and missing momentum experiment that are maybe the latest coming to join the search for this light dark matter in terms of technique to search. So last time we saw that beam dump experiment, dumping this very large amount of charge on a dump can achieve good sensitivities in both the visible and invisible decay scenario for dark matter. But I think that did not say is that this technique has a drawback, in particular for the invisible decay scenario, because there, if you want to use a beam dump experiment to detect light dark matter, you have both to produce it in the dump and then to make it scatter on a detector. That is what, for example, BDX does. And therefore, basically, you're asking for two very rare processes to happen. So you have a production, which is mediated by a dark photon, and so scales as epsilon to the second. And the scattering itself, again, is an elastic scattering mediated by a dark photon, so a rare process itself, scaling as epsilon to the second. So at the end of the day, the number of events that can expect a beam dump experiment searching for light dark matter scales as epsilon to the fourth power. So this means that, for example, you have your experiment and you reach some part of the parameter space and you want to go down by an order of magnitude, you need to acquire 100 times the statistic if you are thinking of a scenario of light dark matter with a y parameter on y. So this raises the question, is it possible to skip the second part of the process? So do you really care to measure, to detect the dark matter scattering in our detector? And the answer comes with the so-called missing energy technique. Here the idea is a bit different. So you have also in this case a thick target, so a target when you completely degrade the energy of your incoming beam. But now it is an active target. That is to say, it measures the energy, so an active beam dump. So the idea is this: you have your beam, you measure before coming to the target its energy, you measure the energy deposited in the target by the particle, impinging particle, and then you look at the difference between two numbers. If the difference is large, it may be that part of the energy has escaped in the form of dark matter particles. So this is a very simple scenario for this kind of experiment. And now you are limited in rate. You cannot just dump high current on your detector because you have to tag every single particle. So you have to give the time to your detector to see the particle which is incoming, measure its energy, then the active target, and this means that you are somehow limited in rate, and also you need a particle beam which is capable of providing particle one at a time, which is not always possible for accelerator. For this kind of experiment, the signal scales now as epsilon to the second, so better than the you gain a factor epsilon to the second to the beam dump, but now you have to face many backgrounds because obviously we saw that for example, in an electromagnetic shower, you produce many standard model particles which are themselves very penetrating, for example, muons, which would escape the detector, and you will have a signature which is similar to that of the dark matter. So this is maybe a kind of background. Also, we produce hadrons and other penetrating particles, but also you may have contaminants in the beam. If you think that this particle is an electron and instead is a hadron, the hadron may interact inside the detector, maybe producing some meson, decaying neutrinos, and then your neutrinos fly away, bringing away a lot of energy, and again, this mimics your signal. So, many challenges to face, and up to now in the world, the only experiment that is using this technique to search for light dark matter is NA64, which is an experiment using the SPS electron beam at CERN H4 line. So, the experiment is located in the north area of CERN, and from this, the not so fancy name NA64. because it is the 64th experiment made in North area. The E here is that is due to the fact that they're using an electron beam, and there is a parallel effort by the same collaboration using a muon beam that you will see in a few minutes, so to distinguish them an A64E and A64 mu. The sketch of experiment is this one. So the active target, the dump itself, is this small part here. All the other, which is an electromagnetic calorimeter, as we will see, all the other components of the detector are just there to be sure, for example, that the particle that is coming is really an electron with 100 GeV, and nothing else is escaping from the calorimeter. And so to veto all the standard model particles that may be produced and escape from the vehicle. So from upstream to downstream, you have a spectrometer composed of some tracking stations, which measure the position of particle, a magnet, again tracking station, and you can measure the momentum of impinging particle, a synchrotronation detector that, as we will see, allowed to distinguish from electrons to hadrons, and then after vehicle a very large hadronic calorimeter to stop all the hadronic particle produced in vehicle or coming from the beam. So this is the general sketch. Here you have a picture, which is this experiment are not really nice to photograph because they are very long, and here you can see this is the target is here. This one is the module of the hadronic calorimeter, and this is the magnet that bends the beam to measure the momentum of the incoming electron. If after all this part, there is also another magnet, because if you produce muon in some part of the chain of the detector, for example, a pair of muons, you can use these muons, divide them with a magnetic field, then you have a tracking station, and you can do some physics with these muons, but I won't talk about this part of the experiment. Okay, so first of all, I told you this experiment is at SPS, which is the same facility where we lost, for example, SHIP, and SHIP we will use a 400 GeV proton beam. So this is the kind of particle you can find in SPS. So from this particle, if you want to use electron, you have to produce electrons, and to do so, the technique is this. So the 400 GeV beam from the SPS impinges on a target which is T2 target of a North area, and from this interaction you produce many particles, hadron, neutrals, electron and positron, and many gammas. And after the target you have some sleeping magnets that bends all particles that are charged, and only the neutral particle goes in a straight line, and within neutrals the main component are photons. Then there is the so-called X-tax, which is just a shielding that has some holes in there, so you can select the kind of particles and then depending by momentum. But we are interested in just the straight going trajectory for photons, because we have here a LED converter, and the LED converts photons in pair of electron and positron, and finally you have your electron beam. Obviously, you can understand that all this change, result in the fact that you may be, for example, some hadron neutrals, which are produced here, that are not bent by the magnet, and then they decay after the magnet in some particles that are contaminant of the beam. So this is basically what happens in this kind of not primary beam, and the result is that you have a contamination depending on what particles you have and you want to operate with. So for example, if you want electrons, you have this contamination, and this is the number of hadrons per number of electron impinging on your experiment. And you can see that at 100 GeV, which is the operation of A64, we have order 0.3% hadrons per each impinging electron. And this is something that has to be accounted for. And to eliminate these contaminants, is the first part of the detector, which is called also the upstream part, is responsible of the particle identification. And we will see now the components of this detector chain. So the tracking station in A64 are made by different detector. One that I want to show you here is the so-called micromegas detector, which is a detector based on this principle. You have a gas enclosed within a surface. The gas is usually a mixture of argon and CO2, and you have two cathodes, one at lower voltage, and when an electron, for example, or any charged particle passes in this region, it is filled with this gas, which is order 5 millimeters, you can have some ionization, and the electron-ion pair travel through this gas up to they reach a second part where they accelerated by a large magnetic field, and they produce an avalanche that basically hits some silicon strips where you can sense the charge, and so you can know where the particle has passed. If you basically use two strips of silicon, two directional strips of silicons, you can reconstruct the impinging position of your particle. This is a picture of what is the detector, and here the result after a long exposure to the beam. You can see the profile of a beam, for example, in this situation. But this is a very broad beam, and you see that the macromega reproduce the shape of it. So after the tracking part, you have the so-called SRD detector, that is the synchrotron radiation detector. So as I said, we need to distinguish between hadrons and electrons, and at this energy, for example, it's impossible to use a Cherenkov detector because all the particles would emit radiation, Cherenkov radiation, basically in the same way, and so we have to rely on something else, and the easiest thing to do is to rely on synchrotron radiation. So since there is a magnet and the electrons are bent to measure their momentum, they emit some synchrotron radiation, which is emitted according to the Larmos formula, depending on the radius of their trajectory, but most of all depending on their gamma to the fourth power. This obviously means that at the same energy, an electron will emit much more synchrotron radiation with respect to an hadron. And then if you detect these photons, you can distinguish between the two kinds of particles. Here you have a profile of a detector, which is basically placed between, here you have the position of the unbent beam, so how the beam should go if there was no magnetic field. Here how the beam passes with a magnetic field, and the photons are emitted along this trajectory, and they hit a detector, which is made by plastic scintillator and LED layers led by photomultipliers, so you can detect this light. And here you have two different spectra, for example, for electron data, also with the comparison with Monte Carlo, you can see it's very good, but also for a data set composed of pions crossing, for a bion beam. You can see that the difference in energy is very large, so that applying a threshold you can reduce in a very effective way your contaminants up to 10 to the minus 4, 10 to the minus 5 in efficiency. You have some pictures of the detector, how it is made. As I said, there are layers of plastic scintillators and LED, many of them order 100 of these layers. The light emitted by the plastic scintillator is conveyed to the PMTs by these many fibers, and so this is the system basically when it is being mounted. Have all these different layers, one on top of the other, which compose the modules of this detector. Okay, this is mainly the most important upstream detector, and then you arrive basically after some tricky station here. For example, you have micromegas, and micromegas. You arrive to the automated calorimeter, which is the heart of the experiment, where the LiDAR matter production, if LiDAR matter exists, occurs, and where you measure basically the missing energy. This is a so-called shashlik calorimeter. Shashlik is a kind of Russian barbecue, where you put your meat and you with some metal rods, and you cook it on fire. And so, since there are some metal rods which hold this cell vehicle, this is the name of the detector. It's basically a series of, again, plastic scintillator and the LED layers, which are then read by these fibers, that inside this module, they are twisted along the center, so that there are no, let's say, dead spot inside the cell. The calorimeter of an A64 is composed from many of these modules. It's 6 by 5 of these modules. And the total length, it is 40 radiation length, that is enough to stop, contain any electromagnetic shower. Here you have, for example, a spectrum of the energy measured by this calorimeter with an impinging positive electron beam of the SPS beam. Here you have a peak of the electron of a primary beam. And you can measure the resolution, which is fair enough for this kind of experiment. And also you can see the contaminant part of the beam. So as I said, there is some fraction of a percent of hadron contaminant. This plot has been performed before any other analysis cut. So here we have both the primary electrons and also the hadron contaminants that they do not deposit all their energy in the vehicle, but they punch through, and therefore you see this shoulder here, and also some very low energy events here. So here, this, if you don't have any other way to react to the event, for you this is, for example, maybe missing energy event, and therefore the background event. Okay, now after vehicle we have the last part, which is the downstream part, which is composed by VITO, 2 VITO muon produced inside the vehicle, and a very large hadronic calorimeter. The VITO is a fairly simple detector. We're talking of 3 layers of plastic scintillator that you can see in the photo here. They are fairly thick because they are about 5 centimeters thick, and they are superimposed, so to don't have dead spot. And they are read by PMTs, and this detector is placed right after the electromagnetic calorimeter. So the important role of this detector is that one of vetoing all the muons which are produced in vehicle and then escape with a lot of energy. Here you have the very nice Landau peak of the muon resulting from the test of this detector. And with this kind of detector you can reach efficiency in rejection of the muon, such as you have only 1 muon in every 10 to the 4 particles. Finally, this is the HCAL, which is again similar technology, but with rougher segmentation. We are again talking about LED and scintillator, and this time iron, because it's very big and LED costs a lot. And then we have optical fibers to bring the light outside the plastic scintillator, and again a PMT readout. We have 4 modules which are basically 1 meter in length, and the main role of this detector is to stop hadrons, and for example neutral hadrons, because we can have a production of neutron with high energy, or neutral mesons too. And for example here we have the plot of what happens when you have a pion impinging on this detector. This is only 1 module, so the energy deposited on 1 module before any normalization, so just the ADC count. And here you can see this peak is when the pion undergoes a hard interaction within the hadronic calorimeter, which results in a hadronic shower that is somehow contained, and so you have a peak at the energy of the pion. But then you have also event where the pion does not undergo any hard interaction in the HCAL, and therefore what happens basically is that it only leaves an ionization track, and this is a dangerous event, because if this was instead of a pion was a neutron, for example, you won't even have this ionization band. So this is a way to evaluate how many hadrons cross the 1 module without having their interaction and depositing their energy. And since this number is order 10 to the minus 3, you can easily evaluate with 4 of these modules in a row, which is the probability to have such an event, which would be the background, and it is basically 10 to the minus 12. So this is a large enough H-cal for an A64. Okay, come now to the analysis of an A64, which has been collecting data since some years. And here is a typical so-called hermeticity plot of an A64. So the analysis is done in that way. Where you apply all the cuts that identify, for example, a clean impinging electron track. So, for example, using information of tracking, you ask for no activity in the veto, and then you do some request regarding the shape of the electromagnetic shower inside the vehicle, which has to be compliant with the typical electromagnetic shower event. And then what remains is this plot here. So the events surviving all the cuts are these. Here you have the energy deposited in the vehicle, and here you have the energy deposited in the H-cal. The signal box for this kind of experiment is an event where you have lost at least half of the initial beam energy, and there is basically no activity inside the H-cal. So what does this thing? These are, for example, neutral hadrons, which are produced in the E-cal, and they, for example, are not detected in the veto, and they arrive to the H-cal, and they deposit some energy in the H-cal. So this is basically an energy conservation band, where some energy was deposited in the E-cal, and some energy was deposited in the H-cal, so the diagonal should be, let's say, from 100 to 100 GeV. It is not to 100 GeV. This is because an A64 has a trigger that requires for an event to be saved to have some missing energy, because otherwise it will save a very large number of events where nothing interesting happens, so just electromagnetic shower of 100 GeV. So you require a threshold of the missing energy at the trigger level that selects somehow more interesting events. So what are the main background for this experiment? You have different possibility. So, for example, the production of a pair of muon in the vehicle, which is lost in the H-cal, and you don't see it in the veto, but also being contaminants, that is to say, hadron and like pions and kaons, they may decay, they misidentified by the upstream part as electron, and then decay as mimicking therefore a signal, but also some lost neutrals that exit the H-cal and so on. But you can see here that all this event or this background result in less than 0.5 event of background, and this is for the last published NA64 data. Here you have an example of so-called sideband fit, which is done to extrapolate one of this kind of background, which is the upstream interaction, which is to say interaction of the electron within some part of the tracking elements. And so what is done, this part background is evaluated from data, extrapolating an exponential distribution towards the signal box. So an important standard model process for the calibration of an A64 experiment is the so-called muon production. So from the point of view of the kinematics, this process, which is the radiation of a pair of muon from an incoming electron, is basically the same than your signal, because instead of from the point of view of the kinematics, obviously. And also from the point of view of the H-cal itself, these events are basically the same to signal events, because muons deposit only a few MEVs inside the vehicle, and therefore you can neglect this energy, and therefore it's like you produce some feebly interacting particle. So you can use this event, you can see accumulated here, for example, to cross-check the simulation, perform studies of the efficiency of the detector for the signal, and so you have a data-driven way between the two states to reduce all the systematics associated to the typical problems of acceptance, efficiency, and Monte Carlo. For example, here you have a comparison between the muon spectrum between data and Monte Carlo, and also for vehicle, and also for vehicle, which the agreement is again quite good. Okay, so this is the result of an A64. The last published result, which are based on a statistics of 10 to the 12 electron target. The experiment observed no signal, so no events with a missing energy larger than 50 GeV after all the application of the different analysis cut. And this result for the scenario where alpha dark is equal to 0,1 already excludes all the thermal relic for the scalar dark matter particle, but also significant part for the Majorana relic. There is also some very small discovery potential, so we excluded a bit of this part of the pseudo-Dirac fermion relic target, and this is due to the resonant annihilation of positrons. So exactly as what we saw yesterday for the Windamp experiment, is an A64, which has a thick target, and therefore you have an electromagnetic shower inside with many positron and electrons inside. You can produce dark photon via resonant annihilation of secondary positron, and this gives you this enhancement in the sensitivity that can allow to explore deepest region of the parameter space. Actually, I don't have to talk about that, but there are ideas of exploit this effect, varying the energy of the beam, because the position of this peak depends on the energy of the beam, to basically scan the parameter space. But unfortunately, I don't have time to talk about it now. Okay, so this was the part regarding the invisible searches of an A64, but an A64 already did also some searches for visible decay of dark photon, and in particular searching for the X17 particles, so the same X17 that could explain the anomaly for the atomic experiment that was searched for by Padme, and so on. So to search for this kind of particle that in the parameter space of interest has this lifetime here, so very short, the setup was slightly changed. The experiment was used not anymore as a missing energy experiment. So we are searching now for a visible decay. So it was introduced a new very small tungsten-based calorimeter, so plastic scintillator and tungsten, and this is the place where the interaction is supposed to happen, and then you can produce a dark photon, your X17, that will decay in electron-positron pair. So after this target here, you have some tracking stations, and then the vehicle itself. So the idea was to see a track here disappearing, and then the decay of electron and positron, and two distinct shower shapes inside the electromagnetic calorimeter. So this was a setup, and the A64 collected some data in 2018, which was enough to exclude some of the parameter space of the so-called beryllium anomaly, or X17. So the plot you saw yesterday when we were discussing about Padme, and that the remaining part of the parameter space that Padme is targeting is here. The exclusion limit on the lower part has been set by an A64. So this is the result. You can see it has a shape of a typical Windamp experiment, and in this case, an A64 is a simple Windamp experiment. So there were also ideas on how to cover the last remaining part of the parameter space. So why it's the limit stops here is not a matter of statistics, but as for all being done, is a matter of lifetime of a particle. The particle is so short-lived that you produce it in your dump, in this case the WCAL, the tungsten calorimeter, and then the electron-positron pair resulting is degraded by the interaction within the dump, and therefore you cannot measure the electron-positron in the electromagnetic calorimeter and the tracking system. So to achieve some sensitivity here, you don't need much more statistic, but you need, first of all, to redesign a bit your apparatus. And the idea in particular is to build a more compact tungsten calorimeter so that you produce your dark photon here, X17, it has enough lifetime to travel this space and decay. Then you apply, you use a vacuum chamber to have your track with magnetic field to divide the tracks and to be able to measure correctly the angle between the electron and positron, and this is a way to overcome the limits of this measurement. So this possibility is being discussed in the collaboration, and probably in the next few years will be adopted to perform a final measurement of this anomaly. Okay, we move now to the parallel effort of an A64E collaboration, A64 collaboration, which is an A64 mu. So exploring the dark sector with a muon beam and not with an electron beam. So why you should use a muon beam instead of an electron beam? The idea is to access to other variations, say to the ladder matter model, that foresee a very weak coupling to electrons, but instead where you have important coupling to second generation lepton, mu and tau, for example. One of these scenario is the so-called L mu minus L tau scenario. I won't go into detail here, but the reason why it is considered very interesting is because it could be an explanation of the so-called G minus 2 anomaly. So this scenario has raised a lot of interest, and the idea of an A64 collaboration was to perform a new measurement with a muon beam to try to exclude this theory, or maybe discover something. But if you want to do such measurement, you cannot use the same exact technique because muons are penetrating, and you cannot simply measure their energy before and then the energy deposited in the vehicle. You have to measure the momentum with a spectrometer after they interacted in your target, and then you perform, that is to say, a missing momentum experiment and not anymore a missing energy experiment. So the detector setup of an A64 mu is different, even if basically the components are all the same. So you have a first spectrometer, which is composed of tracking station for micromegas, straw tubes, micromegas, straw tubes, a bending magnet, some focusing quadruples, and from this first part here tags the beam of muon and defines the initial momentum of the muon, which by the way is 160 GeV from the beam used by an A64 mu. And then you have downstream part, then you have your target vehicle, where you hope the reaction to occur, and it's basically the same thing as the production of a dark photon. We have exception, but now the particle radiating is a muon, not an electron. And then you have another system of magnet and tracking, so another magnetic spectrometer to measure the momentum of the muon. If the muon has undergone such a reaction, it has lost some momentum, and then you receive a bending due to the loss of momentum in this system. So again, not a very beautiful experiment, another experiment in line. This is another region of a North area, and this is the setup. You can see some tracking elements, magnets here, the tracking elements, and this is the calorimeter where the reaction is supposed to happen. And this is the parallel of the hermeticity plot that I showed for an A64E. Now you don't have E-cal versus H-cal, but you have the final momentum of the muon measured by the spectrometer versus the sum of all the energy deposited in the different ECAL in the ECAL system. In particular, the dominant contribution is the ECAL, which is the target where the reaction is supposed to happen. And here again, the signal box is between 0 and 80 momentum, which means that you accept as an event of signal an event where half the momentum of the muon beam was lost. This is the region where the most muons accumulates, since they simply didn't lost any of their momentum, and this is the energy conservation band where the muon undergoes some hard interaction inside the ECAL or the HCALs, and they deposit their energy, and some of the energy therefore is transferred to the HCAL, and when you measure the momentum, you measure a lower momentum. And it's not working anymore. Okay. But again, even in this case, the plot that we're seeing is obtained after applying many analysis cut, and you pass from the, I can say, first raw sample where you collect all events, then you start to put constraints. For example, the first cut is on the timing of the event, so you want to be sure all the signal from the different elements of the detector are in time. Then you clean your sample, asking for a single git per tracker, since if there are many different particles sitting in a tracker, it means that something else has happened. There is a range for the momentum of the impinging particles. Then there is a quality cut on the downstream momentum, and then you want the energy in the ECAL in the VTOLs to be compatible with the MIP, that is to say a muon. And this is the different passes of the analysis. You can see that the spectra of this hermeticity plot cleans at every step, and at the end you are left with clean events, that is to say events where the muon crossed your system. You measure the momentum before, momentum after, and you have no loss of energy. And this again is the signal box. So if you see something here, after you have selected your events, you look into your box, you see something, you expect to have a signal, you call it a signal. This didn't happen in the 2 times 10 to the 12 to the 10 muon target that NA64 mu collected, and this allowed the collaboration to set this very interesting limit on the scenario of the vector-mediated light dark matter, while now it's not anymore a dark photon, which is Z prime, that is to say a particle interacting only to the second generation lepton, in particular with muons. And this result allowed to exclude this one, that is the so-called G-2 band, that is to say that region of the parameter space that could explain the anomaly, the momentum anomaly of the muon, if that was the theory underlying that effect. So this is the result of this experiment, and as a first statistic collected by them, I think is quite good. Okay, but NA64 mu can say something also in the normal dark photon scenario, since obviously if a muon can radiate a Z prime, can also radiate a normal dark photon, and more than that, since the muon are more massive than the electrons, they are the emission of high energy dark photon is favored with respect to an electron beam of the same energy. So if you want to explore, for example, this region of the parameter space with an A64, it's really difficult to do it with electrons, because the cross-section goes down, and here you see the projections that are for the electron part are enough to cover to reach almost the last thermal target, but they're not enough to cover this region. You can cover this region with muons, and this is the projection for muons. Obviously, this is a very optimistic statistics, because you have to collect a lot of data, but this can be considered the final goal for this such of effort. Okay, we finally come to the last experiment we're going to talk about. And this is an experiment that is actually not existing, but will be a future experiment. It has been studied and preliminary studies are being done, which is the so-called LiDAR matter experiment, or LDMX. You can look at this experiment a bit as the ship experiment of the missing momentum. So the state-of-the-art experiment that could bring this technology to the highest level. And the idea is always the idea of measuring a missing momentum, but is a bit more sophisticated, because you don't measure the missing energy in an electromagnetic calorimeter, but you, again, as in the case of muon of an A64 mu, you measure the momentum of the electron that you're using as a beam first and before a thin target. So the target beam energy that you're thinking to use between 4 and 8 GeV, and the signal signature is the result of what you can expect from dark matter production via radiative process such as the A-Strahlung. So a low energy electron which lost a significant transverse momentum. So here you have an information which is also directional with respect to the simple missing energy, where you just measure the energy before and after, and no activity in all the other part of the experiment, which are an electromagnetic electronic calorimeter and electronic calorimeter, where you expect to measure only the low energy electron. So the sketch is basically this. You have a magnetic field between the tracking station before and after the target, so you can measure the momentum of the impinging particle and of the exiting particle, which is always an electron. And so that's the strategy that itself is not really complicated, but it's true that there are very challenging technological things to overcome, and I will discuss about that. So the LDMX experiment will be realized at SLAC, which is Stanford Linear Accelerator Center in California. And this is the host of the linear accelerator of SLAC, which you can see here, but also of what was the PEP-2 collider, where Babar was placed. So we talk about Babar, now you can see where Babar was located. And actually, the beam line that links the LINAC, the linear accelerator that we will use by an A64, and the experimental hall, which is and the station A here, does not exist for now. So this is something that has still to be built, but there is a project and already an idea on how to transport the beam to this facility. As you can see here, this is the part that it still does not exist, this part here, so this is something that has to be done. And the facility will allow to provide a very low current beam, so one particle impinging at a time, which is what you want for such an experiment, but with a very high repetition rate of 37 megahertz, which means that you want to perform a missing momentum experiment at this rate. You have basically to measure particles every 27 nanoseconds. So this is really challenging. It's probably the most challenging aspect of the experiment. So here you have some plots that show the strength of measuring the missing momentum of the electron instead of measuring only the missing energy, because here you have the plots from simulation of the missing momentum, the recoil energy of the electron scattered after the production of a dark matter particle for different masses. And here you have what comes, for example, from regular Bremsstrahlung. So an electron scattered via regular Bremsstrahlung has a distribution. And as you can see, for all the masses, there are important regions of this plot that are in common between the two processes, which means that whatever cut you place on your recoil energy of electrons of electron, you will have some background from, for example, a reactive process such as Bremsstrahlung. Obviously, providing that you don't see the photon, but this is just a conservative idea. Otherwise, if you look at the transverse momentum of the electron, you will see that for the regular Bremsstrahlung, this quantity is almost always 0, while instead for lighter matter, the momentum distribution has a significant, unobservable quantity, because obviously lighter matter is light but has mass, and so there is a kinematic difference. And if you go down and down with masses, so at the 10 MeV, you can see that this goes in the direction of the background, so you will have less rejection power if you were to come to other effects. But still, this is the proof of how measuring the missing transverse momentum is really something that can give you help in rejecting the background for this experiment. So here you have a sketch of the detector. The scale, as you can see, is not particularly big. We are talking of 4 or 8 GeV beam energy, so you really have to contain an energy which is not incredibly large. And so you have the first part here, you can see, is the tracking part, where the tracking system are placed together with the target where reaction occurs. This is enclosed in a magnet for the measurement of the momentum.
Luca?
And then you have a system which has to
Hello?
be very...
Hi, Luca. I had a question on the previous plot.
Yeah.
Could you explain a bit more the Bremsstrahlung process of the particles you're working with? Because as far as I understood, it was more something you had into account for the muon, because of you cannot like detect it very easily in the electric colorimeter, so that's why you had like sometimes big muon detectors, but now you're using it for the electron too, I think. So how, like, what's the process? What are you trying to
So the idea here is that we are talking, I still didn't say it, but their target in thermostatistic is 10 to the 16. So you want to control what's happening in your detector to a very, very precise level, and you want to have no possible weird background entering your signal window. So whatever handle you have to distinguish between LiDAR matter production event and something else which is standard model, you want to use it. So missing energy itself, which for example in X64 use, is an information, so is the information that some energy was lost, but maybe not enough, because you may have some standard model process, very rare for example, that gives you a missing energy without at the same time you think this is dark matter. So here you have the comparison between the recoil energy of an electron which has okay. So let's assume that an electron, instead of doing A prime Strahlung, you have normal Bremsstrahlung, okay? So you have a photon, Bremsstrahlung photon, and your recoil electron, okay? But this is very common process. So in 10 to the 16 electron target will happen many times, okay? Many times. So it may happen for some time, maybe, that you are losing the radiated photon for some reason. You are inefficient in your detector. It's really complicated to control things up to such a very, very large number of events. So you remain with an electron in your detector, which has been scattered, okay, and it's lost energy because it has produced a photon that you have lost. So here, just relying on the missing energy, you will not able to distinguish between the dark matter and this is a weird event, but in 10 to the 16, maybe something can happen. Instead, if you, instead of looking, at the missing energy, or basically the energy of the scattered particle when it's bound to the missing energy, but you look at the momentum, you can see that there is a significant difference, because you expect the transverse momentum of a recoil electron from dark matter to be significantly larger, and for normal Bremsstrahlung, the electron just goes straight. So this is the reason why this helps. It's not the only thing, obviously, but this is just to give you an idea of how. But it's intuitive. You have basically more information. You have a three-dimensional information instead. You miss the momentum instead of missing an energy, which is just only one number. So.
Yeah. Thank you.
Okay, so I was describing the detector. This is, as I said, after the target, you have a calorimeter to measure the energy of the scattered electron, and around the calorimeter you have a very, very thick hadron calorimeter, which has the aim to detect, for example, again, as in the A64 case, hadrons or particles and ephesus in interaction. You have to understand here that this large number, we have to think of very, very weird standard model processes where is the result in a background, and I will see some in a second. So I will now talk about the two most interesting detectors, which are the tracking error and the calorimeter. The tracking follows the same technology as what was used by HPS. In fact, these are the same people building the HPS tracking system and this system, and this is based on silicon strips. We have two stations, one before the target and one after the target, which by the way is tungsten, 0.1 radiation length. So the material budget of this detector is very low, and this is good because you don't want any, for example, hard interaction of initial electron happen here, or at least you want to be able to distinguish. So after the target, you have six layers of these trackers, and this allow to reconstruct the momentum of a recoil particle with good efficiency between 50 MeV and 1.2 GeV. So the target is 0.1 radiation length, and this is just a compromise, because on one side, if you increase the thickness of target, you will have potentially more interaction and therefore produce more dark matter events, so a larger yield of produced dark matter. And on the other side, this may result in multiple interaction, degrading the energy and bringing to background events, and so this was chosen as a good compromise. The magnetic field, as I said, surrounds both the tracking dedicated to the incoming particle, which is called the so-called trigger tracking, and the recoil part of the tracker, so you can measure the momentum of the particles. Okay, this is instead the vehicle, which is something very different from what we saw in all these experiments we have discussed up to now. So they need something very fast, because as I said, they want to go to up to 27 nanoseconds per particle, and they want something that is really radiation hard, because you are making many particles impinge on your detector. And for this aim, they're thinking of something a bit different from the classical scintillating crystal or plastic scintillator, which is this sampling calorimeter made of silicon and tungsten buffer. So this is a sophisticated detector that behaves a bit like a series of tracking detectors. To say, it measures the flow of particles through each of its plane, and you have many of these planes stacked one on top of the other, and basically for an impinging particle, you can basically reconstruct the event with a very, very important precision, and this is a very, as I said, very fast detector. So, and this is fast, it has to be fast also because vehicle will be part of a trigger of experiment. So you have to trigger 27 nanoseconds and you need something fast. So this is something quite top-notch and state-of-the-art regarding what you can do with this kind of measurement. Okay, here you have the summary of some studies that have been performed by the collaboration to try to see to study what are the dangerous background of such an experiment. So you are going up to the 10 to the 16 level, that is to say you are making your 10 to the 16 particle impinge on the detector, and so you have for sure you will have some very common event, so production of Bremsstrahlung, Trident, and so on. But also, the down you go, up you go in statistic, you see things more and more strange and processes of standard model, which are also less studied. So we tried to make a list of all these processes. I won't go into detail here of everything, but they thought also for each of these background which are the handles that they can use to reject them. So you have many possibilities that are shown here, and depending on the kind of event, they think they hope to be able to arrive at a zero background measurement. They stop at 10 to the 16 also because they expect neutrino processes at point are irreducible, where you produce neutrino and you have no way to distinguish from so again another neutrino floor for accelerator experiment. So you can see that 10 to 16 is enough to have a reasonable reach for this experiment. This is a simulation, obviously, and shows what is the projected sensitivity for this experiment in a first phase and in a second phase, which changes depending on the statistics. So the first one is a bit more achievable, it's 10 to the 14, and you have some differences depending of the kind of beam you were going to use. And then you have the phase 2, the upper limit to the upper limit, that is to say 10 to the 16 electron target, that corresponds also to many years of taking data. So very challenging but also very good result. Here there was some different curves that represent the variation in efficiency depending for example, the discovery of some background events. So if I were not to be able to run the experiment at a zero level background, for example, we will have 5 of 10 events of background. This is how the upper limit would change. So you can see it will still be very good. So since this is my last talk, I just want to wrap up things a bit and to discuss. To summarize what we have discussed in these four lectures. So I hope I convinced you that vector-mediated LiDAR matter is an interesting model to explore, since it gives rise to a very rich phenomenology, which foresees particles which are very long-lived, very short-lived, that can decay to particles of a standard model, that can decay invisibly, and this has brought to many different experimental approaches to explore these scenarios. And we saw searches at colliders that, for example, in a visible scenario comes from the up of a parameter space, but also has some possibility to perform some displaced vertex searches. The same for thin target, and we also saw beam dumps, which have this shape due to the fact that they are limited not by the coupling itself in terms of number of particles produced, but by the fact that the particle decay inside the beam dump itself that cannot be measured. So this is for the visible. For the invisible, the same. We saw the case of Babar, and for now, one of the most, or I say the most important limits set by NA64 in this invisible scenario. So this is the status now, but there will be many new things coming in the future. First of all, SHIP, LDMX, that will probably explore very intensely this parameter space. So who knows? Next year we may have some good news. Let's hope for it. And with this, I conclude. Thanks to you for the attention, and I'm open to questions.
Questions? Okay.
So I have one very simple question. So when you mentioned the production and detection of dark matter, then you had the epsilon square.
Yeah.
And then when you say that we go to missing energy, my understanding was that you have just epsilon because you have to produce it, but there was an epsilon square, so I got a bit puzzled.
No, we have epsilon square and epsilon square.
Yeah.
Yeah, let me. So here is epsilon square here and epsilon square here. So epsilon to the
Oh,
fourth.
epsilon the fourth. Okay, great, thanks.
So that's the reason
Yes,
why
yes,
you
yes,
need
yes,
to take. Okay.
Thanks.
Yeah, and back to your final slide, sorry, you skip around.
Okay, no problem.
But yeah, so in the summary plot on the visible dark matter, yeah, so you have like all these beam dumps on the bottom left, which are basically limited by the lifetime of the particle. And then you have like a bunch of CMS collider type experiments like at high mass. What do you think is the best strategy for covering that red band? Is it somehow like collider CMS style experiments, or somehow higher energy beam dumps?
Yeah, I think that we have to weigh. Maybe the most promising one is the displaced vertex, and this can be done both at Accelerator and at fixed targets. Unfortunately, it's not here, but maybe remember the projected sensitivity for HPS, which is a very small thin target experiment, which is here, so it has some discovery potential.
Yeah, so you can cover a lot of that parameter space, from just like reanalysis of current detectors, or would you need more detectors?
I think you need to go on with also the collider. I expect some changes to be done, because often what happens is that the searches from collider are limited by triggers, because they were not thought to search for this kind of particles. So basically you lose your efficiency due to the fact that you did not save that event. And so I expect for iLumi, for example, to have interesting news from the point of view. So I think in any case, a different strategy is the good answer, so the right answer.
Yeah, okay, perfect, thanks.
Okay, so since this was Luca's last talk at our school, thank you very much, Luca, for accepting our invitation and for providing us with this great set of talks on light dark matter. So please, everyone, a warm round of applause to Luca.
Thanks.
And it's time for a coffee break. We'll be back at 11:30.